Yes. So today we will discuss OS system structures here. Yes. So today in our class we'll discuss OS system structure. The objective behind learning in this class to describe the services an operating system provides to users, processors, and other systems. To discuss the various ways of structuring an operating system. To explain how operating systems are installed and customized, and how they boot. So coming to operating system services here, the operating system provides an environment, as you know, for the execution of the programs. It provides certain services to programs, users of those programs. Basically, two types of services that it provides. One is set of operating system services that provides which functions that are helpful rather to the user, and set of operating system function for ensuring efficient operation of the system itself via the resource sharing. So these are the two type of services that operating system provides for us. Now coming to the how operating system services are helpful for the user, user interface. It provides you an interface here. The different kind of interfaces that you can see across different kind of operating system, command level interface and graphical level interface and batch interface, right? So if you look at command line interface, where you find the dollar prompt, where you can probably use some text commands in order to invoke the services operating system, right? So the help of keyboard, you do that, right? And graphical user interface, where you find icons, the services available in the form of icons. By just clicking on that respective icons, you can able to invoke the services. And the batch interfaces, that are commands and directives to control those commands are entered into files, and those files are going to be executed here one after the other. Some system provide two or all three of these variations. For example, Unix operating system will provide you both CLI and GUI kind, right? And another kind of service that operating system provides is a program execution environment. It provides you an environment where you can execute a program. The system must be able to load a program in order to execute the program into the memory and to run that respective program. Fine, and thereby the program is going to be executed either normally or abnormally if an error indicates or an error is rather raised, right? IO operations. It helps you to provide. It helps to give you a kind of environment where you can have interaction with IO and then carry out the IO operations. A running program may require an IO, probably from keyboard certain time or from file rather, right? Which may involve a file or an IO device, right? So in order to get that services rather served, we have an interrupt service routine, which is going to be rather invoked, when such kind of necessities are raised. And further, seeing what kind of services operating system provides, like a file system manipulation. The programs need to read the files and write into the file and create certain directories and delete them and probably search them or list some file information, or you want to give some permission to the file or manage the permissions of the files, that you can do with the help of the file system manipulation. And communication, to have the communication among the processes, to exchange the information, right? It could be between the computers or over a network rather, right? So that can be done with the help of via shared memory or by sending simple messages rather, right? We'll probably see as part of the different kind of services or mechanisms that we have. As part of it, we can probably implement these kind of services like shared memory pipes and system called socket, socket system. Basically, when you are trying to exchange the services with the network, then you need sockets between the computers where you have an intranet connected with this computers. You can probably go with shared memory pipes, you know, uh, and message passing kind. Error detection. OS needs to be constantly aware of possible errors that are encountered over the system, and so that it could able to alert the system, and thereby it can stop the devices from where such kind of errors have been rather raised. Debugging facilities can greatly enhance the users and programmers' ability to efficiently use the system. Resource allocation is another important service that operating system provides, right? As in when you require, the different kind of resources that are available on your system. Like for example, CPU or memory or storage, I/O devices. These are going to be rather allocated as and when required in order to carry out your task. And another kind of service that is in accounting, rather, right? To keep track of which user use how much and what kind of computer resources is also required to be accounted. Protection and security. Two owners of the information stored in a multi-user or a network computer system may want to control use of the information. The concurrent process should not interfere with each other, rather, right? So, in order to protect the computer resources from other, when probably all are connected with the same kind of internet, then these kind of services are very much essential. Protection involves ensuring that all accesses to the system resources is controlled. Security of the system from outsiders requires user authentication extends to defending external I/O devices from invalid access against. Right, different internal, external kind of attacks like denial of service, spam, or malware. These kind of attacks from being protected. You need security services which are going to be provided as part of your operating system. If you look at the view of operating system services, we can see here, you know, hardware lying at the end, at the bottom. There you can find user is at the other end, right? So between the user and the hardware, this is what you have the interface, right? You have GUI, batch, and command line. These are the three type of interfaces, user interfaces, with the help of which the users can interact with the operating system services. These are the different kind of services that operating system is providing. As I said, program execution. In order to execute the program, you need an environment, right? That environment is going to be created for your program to be executed. IO operates in order to communicate with IO devices and file system services, communicating with other computers, resource allocation, accounting, and error detection, protection, and security. There are different kind of services that operating system provides. So with the help of system calls, of course, rather, right? So the user is going to interact the operating system with the help of either of these interfaces, GUI or command line interface or batch interface. Then the system calls will help you to provide all these kind of services as and when required. Uh, you know, um, so the operating system is providing you an environment, we can say, right? It is providing you an environment, so wherein you can probably perform all such kind of services like executing a program and interacting with IO, interacting with file, or communicating with network devices, and getting required resources allocated in order to carry out your task. So these are all the services are going to be provided as part of environment by the operating system, right? Command level interface. Basically, you may have already seen. When you open a shell, there is a terminal, right? You open a terminal, via terminal. So there you find a dollar prompt, which is nothing but a command, right? Shell. We say it's a bourne shell or conch shell, based on the manufacturer over there. So there you can probably give certain commands like ls list out list out the files that are available in this particular directory. Basically, you find a home directory, right? and in that home directory, probably the subdirectories you find. You may create your own directories, right? Uh, and then once you enter, how do you enter into your respective directory? By using cd command, right? Change directory command. SN to look into what kind of directory you are now. You have a present working directory command. So these are all what? These are all the device driver programs, right? So these are all the commands, right? With the help of which you are invoking the services, right? So in order to know present working directory, in order to change the directory, and to list the files, in order to move the files, rename the files, you have mv command, right? Make directory to create a directory kind. These are all basically the services that we are invoking with the help of command line interface, right? CLI kind. Okay. So you can see here the environment it looks like this. You open the terminal. So on this dollar symbol, you can see here you will list out the commands, yes or no. So ls to list out the files, like so, present working directory to know the directory in which you are right now. Fine. So for these kind of things, probably you use this CLI, right? A dollar prompt. A dollar prompt you will be entering your commands and thereby invoking the services. This kind of interface is said to be CLI, command line interface, right? Then coming to graphical user interface, basically when you open Ubuntu, you must have seen first the graphical user interface itself, right? Where you find icons, yes or no? You find icons. So just by clicking this icons is a kind of figure basically which is representing that respective files or programs, right? Actions. So by just clicking with the help of a mouse, right, you are able to invoke those respective services. Yes, sir. So many systems new now include both, of course, CLI and GUI services are available. Like in Microsoft, also you have both this Apple OS. You will probably look at Unix or Linux. Initially, it was only CLI. Now you got GUI, right? And now in mobile systems, you got touch screen interfaces, rather, right? So where you can probably see by just touching this respective icons, you are able to invoke the services. So these are generally deployed in touchscreen laptop also. You got touchscreen laptops are also available, and most of the mobiles are touchscreen, rather, right? So you just have to touch it either with your finger or any pen type also. You have a pen kind of, or you have voice commands also available, rather, right? You can give some voice text, it will invoke the services for you, rather, right? Your Bixby command you have, right? If you install Bixby services on your operating system, you just give a voice command telling it to open the Gmail. It will open your Gmail. Open contacts. Just say open contacts. It will open the contact. Just it will be voice commands, right? So Mac OS with GUI features you can probably find like this, very similar to that of Windows kind. Now coming to system calls, right? What is system call basically? Um, it's a service, which is being provided by the operating system, right? Programming interface to the service provided by the operating system. So it's a interface, programming interface, typically written in a high-level language like C or C++, mostly accessed by the programs via a high-level application programming interface rather than direct system calls. Three most common APIs that you probably find are Win32 API, which is used in Windows, and POSIX. POSIX we are going to use as part of our lab because we are running in Linux, right, or Unix. So POSIX are POSIX-based systems. We see it in Linux, and Java API in Java Virtual Machine. Right? Your Android is basically implemented with the help of Dalvik Virtual Machine, where you find Java APIs being used, right? Now to invoke such kind of services there. Examples of system calls, system call sequence to copy to the content of one file to another file, acquiring an input file name, writing prompt to screen, accepting input, acquire output file name, open the input file, creating an output file. These are all probably you can see the sequence of system calls that you can give as part of a file rather, right? All these commands are going to be executed in sequence one after the other if you give it as a form of a file. Example of standard APIs, application program interface, you can find the function name and the parameters you can pass, what kind of value that it returns. You can use as part of the program also, right? As part of the program, you can use this API services. System call implementation. Typically, a number is associated with each system call. System call interface maintains a table index according to these numbers. The system call interface invokes the intended system call in OS kernel and returns the status of the system call and any return values. The caller need not know a thing about how the system call is implemented. Just needs to obey the APIs and understand what the OS will do as a result call. Most details of the OS interface hidden from the programmer by APIs managed by runtime support library. Set of functions built in to libraries included with libraries. With compilers. The handling of user application invoking the open system call. You can see between the user mode and the kernel mode, you have a system call interface. So user application will open that respective system call. Okay, and this system call interface will help you to open all such kind of commands or that system call as part of what kind of services that it's going to provide you is going to be done and then written. So, as I said, system call is a programming interface, right? To invoke the services, to invoke that operating system services. So an open, command is going to be initiated from the user mode to that respective system call. Then that system call is going to provide the services by running in the kernel mode and then return the respective values back to the user mode. System call parameter passing. We can pass the parameters in system calls. Often more information is required than simply identity of desired system call. Sometimes when you're working with inter-process communication, creating a new process kind of thing, right? Or sending some information from one system to another over a network rather, right? Using remote procedure call and all kind of thing, where you need some parameters to be passed. Three general methods used to pass parameters to the OSS. Simplest is pass the parameters in registers. In some cases, maybe more parameters than the register. Parameters stored in block or table in memory and address of block passed as a parameter in the register. This approach is taken by the Linux and Solaris, of course. Parameters can be placed or pushed onto the stack. This is another approach by the program and the propped up the start by the operating system. Block and start methods do not limit the number or length of the parameters being passed. One method is simply putting it in the register, and the registers are going to be register address is going to be sent. Another one is pushing onto the stack, and then um, you know the stack address is going to be passed. So parameter passing here via the table, if you probably look at, you put the information in the register here. Okay, so X is passing certain parameter to the operating system while invoking that respective service. As part of the service, that our parameters are going to be passed here. So the register is opened, there the information is stored, and that information will pass to that respective operating system call, right? And once it is done with, then the information that it has to return, that it will return into the same, and then from the same, it can rather, you know, take the data. Type of system calls that you find as part of different services. They can be grouped based on the category process control. When the system calls are being implemented as part of the process management, they can be called as process control. They're implemented as part of the file management, file manipulation. They're implemented as part of the device manipulation, information maintenance, communication, and protection. As part of process control, if you probably look at the different kind of system calls that are available as part of the operating system to provide you the services to create a process, terminate a process. Because in order to uh, run the process, you need to first create the process, right? Once it finishes, you need to terminate the process or exit the process. End and abort, because as part of the process life cycle, we'll see the different kind of states in which a process has to take a transition with, for which you need the different kind of services like end and abort, load, execute, get process attributes, set process attributes, wait for time, wait event, signal event, allocate and free memory, dump memory if error, a debugger for determining bugs, single step execution, logs for managing access to shared data between the. As part of the process management in the second unit, probably we'll see all this system calls in details. And as part of our programs, lab programs, we'll implement these services as well. Then coming to file management, as part of file management, the different kind of system calls that are available here, like create file, delete file, open and close the file, read write reposition, get and set file attributes. As part of device management, the system calls that are being provided are request device, release device, read write reposition, get device attribute, set device attribute, logically attach or detach services. As part of information maintenance, the different kind of system services calls that are available as part of OS are get time date, get system date, set system date, get and set process file or device attributes. As part of communication, right, inter-process communication are via the network as well. The system calls that are available as part of our OS are create, delete the processes to communicate over the network. Message passing models are being implemented here with the help of send and receive. Shared memory, as I said, one kind of thing, and to create and gain access to the memory regions. Transfer status information, attach and detach remote systems. As part of protection, control access to resources, get and set permission, allow and deny user accesses, system calls. Now, looking at from the Windows and Unix perspective, these different kind of system calls are available as part of the different services. If you look at process control, in Windows we have create process, where in Unix we call it as fork, right? Yeah, since we are implementing our lab programs using Unix, you can probably see while creating a child program, we'll be using this fork system call. Exit process to exit. We have in Windows, we say wait for single object. We have a wait here, right? In order to make other process to be waited, because generally the main process is from where the execution terminates. So before it get terminates, all other child processes have to be terminated. So we generally call this wait system call in main. for all such kind of child processes to be executed. As part of file manipulation, you can see under Windows we have create file. In Unix we have open. Windows we have read file. Similarly, in Unix we have read, write file. We have write, close hand file, close. Similarly, as part of device manipulation, information maintenance, communication, protection, the different kind of system calls available as part of Windows and Linux are listed out here. Now coming to standard C library, C program invoking printf library call, which calls to write. Actually, in C you say printf, right? But then it is being implemented with the help of a system called write, right? That is available in your, that's going to run in the operating system, right? Write is a system call which is going to be executed in the kernel mode. You are saying printf, right? So actually, this printf is available in stdio.h. This is written by the C developer, rather, right? The person who wrote the compiler of C language, right? Yes or no? But then he must have written stating that this printf will have to open this write system call, right? Only then that write system call is being invoked, and then providing the services like printing this greeting onto the output device. Yes or no? This output device is a resource which is required to be accessed here, right? With this write, and then it is printing this greeting on. So this is all as part of your, you know, OS services is going to be done, but for which the program is already written as part of the compiler. System programs provides a convenient environment for program development and execution. Some of them are simply user interface to system calls, others are considerably more complex. They can be divided into file manipulation, status information sometimes stored in a file modification, programming language support, program loading and execution, communication, background services, application programs. Most users' view of the operating system is defined by the system program, not the actual system call. System programs like file management, and as part of the file management, the different system program available are create, delete, copy, rename, print, dump, list, and generally the manipulated to manipulate the files and directories, right? Status information to be maintained here. Some program asks the system for information, date, time, amount of available memory, disk space, number of users. Other program provide detailed information like logging and debugging information. These programs typically this program format and print the output to the terminal or the output or the other output devices. Some system implements a registry used to store and retrieve the configuration information. In addition to this, services, the status information when requested by the user, it's also required to be rather maintained by making use of different kind of services. It will provide you. They're all part of the system programs, right? File modification, you probably look at text editor to open and then create and modify the files. You need special commands to search content of files or perform transformation of the text and all. For that, you need some programming language support, right? Like a compiler, assembler, debugger, interpreter. Sometimes, these are all as part of the system programs. Program loading and execution, absolute loader, relocatable loader, linkage, editor, overlay, editor, debugging system for high level and machine language. These are all, are required, of course, in order to execute the program. So providing the environment and allowing you to develop your program and execute all that. It's not just providing the environment to execute the program, but as well develop the program as well. Okay, you need all this text linkage editors. You need editors also part of APS, right? Communication that provides the mechanism for creating virtual connection among the process user and computer system, allows user to send messages to one another screens, browse pages, send electronic mail messages, log in remotely, transfer files from one machine to another. Background services like launch at the boot time, uh, some for system startup, then terminate system, some for system boot and shutdown, right? To switch on the system while you are switching on the system, right? As I said, Bootstrap loader program which probably runs well. Then it provides certain services which runs in the background all the time to provide you certain services, right? Those services, as known as demands, as we said, right? Application programs, they don't pertain to systems. They run by server users, not typically considered a part of OS, of course, right? Application programs. Some of the APIs, they will be, of course, launched by the command line or through mouse click or finger poke, but they're not part of the operating system sometimes. Operating system design and implementation. Design and implementation of OS not solvable, but some approaches have been proven successful. Infrastructure of different operating system can vary widely. Start and design by defining goal and specification. Affected by choice of hardware type of system, batch time, sharing, single user, multi-user, distributed time. Two groups in terms of defining goals is one is user goal and another one is system goal. User goal is to get the operating system uh, which can provide the convenient environment to use his services, implement his services, easy to learn, reliable, safe, and fast. System goal point of view, operating system should be easy to design, implement, and maintain, as well as flexible, reliable, error-free, and efficient. Specifying and designing an OS is highly creative task of software engineering. Mechanisms and policies, important principles to support policy, what will be done, right? Mechanism, how to do it. These are to be rather taken into consideration while designing the operating system. Mechanism determine how to do something. Policies decide what will be done. The separation of policy from mechanism is a very important principle. It allows maximum flexibility if policy decisions are to be changed later. Implementation. Much variation has taken place. In early operating system, they were written in assembly languages. Now they are written like using C and C++. In mid, of course, Algol and this algorithmic language, PL by Varada. Actually, if you look at it's a use of mix of languages, right? Lowest level in assembly, main body in C, and system programs in C, C++. Some scripting languages are also being used, like Perl, Python, shell scripts as well. High level languages easier to port to other hardware, but slower if you are writing in high level. Emulation can allow an OS to run on non-native hardware. OS structure, if you will look at various ways to structure an OS is monolithic structure, and you have layered one and macro kernel. So in monolithic, you find these are some of the examples: MS-DOS, disk operating system, and more complex is Unix and then Linux. And a layered an abstraction, you find a different layer. You have called it as middle layer architectures, right? Basically, your Android OS kind, right? Mobile operating systems are being developed using this layered and macro kernel. Between 82 83, you must have found this monolithic architecture. One of such kind is the disk operating system, right? It's a single task operating system. You can run the jobs one after the other. You have ROM BIOS, right? The operating system programs are available here. With the help of device drivers, they will be loaded into the resident operating system, and they are going to be invoked by the application program to run those services. Unix, the original Unix operating system is limited, having limited structuring and was limited by hardware functionality as well. Unix OS consists of two separable parts: system programs and kernels, right? So kernel consists of everything below the system called interface and above the physical hardware. It provides the file system, CPU scheduling, memory management, and other operating system functions, a large number of functions for one level. Traditional Unix system structure, if you probably look at, where you can find at the bottom, you have the controller, device controllers, memory controllers, right? They are just like an interface, right, which are going to rather communicate with the commands that are given by this OS to with the devices that they are connected with. It could be memory or peripherals and all. Then you find a kernel. This is a kernel interface to the hardware, right? And above which you find the signals, terminal handling, I/O system, device drivers, and I/O system, disk and tape drivers, CPU scheduling, page replacement algorithm, demand paging, virtual memory for memory management, and above which you can probably find system call interface to the kernel. Then above which you find the shell commands, compiler interface. They are said to be the APIs from the user point of view. Then you find the users, right? If you look at Linux system structure, at the bottom you find the hardware. Then you have the device drivers, right? Above which you find the file system. The other side you find CPU scheduler, memory manager, character device, and then you have a system call interface. So these system call interfaces are going to be opened with the help of certain APIs here as part of the libraries, and then you find the user. Modularity. The monolithic approach results in a situation where changes to one part of the system can have wide-ranging effects to other parts. Alternatively, we can design system where the operating system is divided into separate smaller components that have specific and limited functionality. The sum of all these components comprises the kernel. The advantage of this modular approach is that changes in one component only affect that component and no others, allowing system implements more freedom, more change when changing the inner working of the system and in creating modular operating system. So by dividing the services into modules, advantages when you change in one module, it will not affect the other one, rather, right? So in layered approach, you can find at the center the hardware is a layer zero. Then you have layers above it. You have, drivers, interfaces, kernel interfaces, middleware architectures, APIs, and then user and all. So you can have any number of layers as when the operating system is growing from internet and the latest cloud point of view. You could find a lot of layers in between. A typical operating system layer, say layer M, consists of data structures and a set of routines that can be invoked by higher level layers. M in turn can invoke the operation on lower level layers. Each layer is implemented only with operation provided by lower level layers. A layer does not need to know how these operations are implemented. It needs to know only what these operations do. The main advantage of layered approach is simplicity of construction and debugging. The layers are selected so that each uses this function, operation and services of only lower level layers. This approach simplifies debugging and system verification. The first layer can be debugged without any concern of the rest of the system. Once the first layer is debugged, its correct functioning can be assumed while the second layer is debugged and so on. If an error is found during the debugging of particular layer, the error must be on that layer. I will stop here and we'll probably continue this microkernel system architecture in the next class.